Hey, this is OXDF, and we're looking at the advent of code 2015, day 23, opening the Turing lock. So let's take a look at the challenge. This is one of those challenges which I think we'll see a bunch over the years doing advent of code, where we are implementing a small computer or small virtual machine. This computer supports 2 registers, 6 instructions, truly state of the art. The registers are named A and B and can have any non-negative integer, begin with the value 0. The instructions are half a register, so round it, take a register and cut it in half. Triple a register, so take a register and triple the value. Increment a register, add 1 to it. Jump to an offset, so continue to an offset relative to itself, and that can be positive or negative. Jump if even, so it's like a jump, but only if the given register is even. Otherwise, just continue to the next instruction. Jump if 1, so make sure it says not odd. If the register is 1, jump to the offset. And that's basically it. They're going to give us a series of instructions, and we need to know what is the value in register B when our puzzle input is complete. So before I go to the challenge itself, I wanted to take a chance. I use this challenge to really dive in on Enums. And so an Enum is sort of a way of combining types or pieces of things that should be grouped together. So they show like a simple enum could be like first variant. You're always going to have either first, second, or third variant, or you're always going to have a location that's either unknown, anonymous, or known with a coordinate passed in. And then you can have these more complex examples. This is the Rust documents page. There's also a page in the Rust book, which is useful. So they use this example of like, hey, you have an IP address kind, and it can either be v4 or v6. That's it, right? There are no really other versions of IP in use. And then they show an example down here where they say, okay, we're going to have an IP address kind, and we're going to have an IP address, and we will that'll take a kind and a string, and they create those things. But that's just, they're really doing this to show you don't actually have to do that, because you can have the enum, define it so that the v4 and v6 take strings, and now you can just, with just the enum itself, you can say it's either going to be a v4 or a v6, and then you give it the string to hold the value localhost, in this example. But you can do even more cool stuff here. You don't have to have them be the same. So v4 can take 4 8-bit integers, which is how we typically think of IPv4 addresses. Or you can have in v6 just take a string, because you wouldn't want to give it, is it 64? Just be a lot of U8s to type in there. Maybe just, and we think of v6 as strings, so that makes more sense maybe. The other thing that's kind of cool, well, here, so this example actually shows it another way. You can think of a message, like something a program is passing to a game or something. And the message might be quit, it might be moved to a new position, it might be write some string to the screen, or it might be change color. And those all do completely different things, but you group them together so you can say, I want to listen for a message, and then I want to maybe match on that message, and here's my 4 options and how to parse them. Cool example they give us actually is option is an enum. And I often, when I get options back, I often just quickly type dot unwrap, right? But the idea here is, an option just either returns none or it returns some and the value inside of it. And so when I do unwrap real quickly, what I'm really doing is saying, I expect there to be a value here. Give me the value inside. And if it actually is none and it's not some, throw a panic and throw an error, because I should have gotten a value here. More responsible programming would probably be doing checking to see like, oh, if this is none, do this, if else do that. Or I had a while loop in a program a few days ago, where I was doing a while popping off a vector, might have been yesterday. And when I get back none, the while loop just ends. Otherwise, it continues, and I could reuse the value inside. So enums are incredibly powerful actually, and we're gonna use them today. Over in VS Code, I'm going to start with my Genday script for J23. I went over this in the day 0 intro video, but the short version is it gives me my input.text. It's got my cookie, so I can just download my specific data, and it gives me a stub to start working off of. And a stub that already has errors in it. Nope. Okay, we're good. So let's start with making some of our data structures. I'm going to sort of build this from the ground up. First thing we're going to do is we're going to make an enum called register, and our registers are either going to be A or B, and that's basically it, right? So now we have a way to refer to our registers. And so now let's make an enum called instruction. And our instruction, where's our, pull up our challenge here and grab these, is going to be one of these 6 things. So let's grab this, paste it here. And so our instruction will be half, and that takes a register. Could be triple, and that takes a register. It could be increment, that takes a register. Could be jump, and that takes an offset. When offset we're going to think of as an I size, because probably I size is too huge, but it's got to be signed because we can go plus or minus. Let's see, let's make a little more space here. We need a jump if even, and that takes a register and an offset. So I guess we'll make that an I size as well. And then finally we need a jump if one, and that takes a register and an I size, and not an is feature detected. There we go. And I think we have 1, 2, 3, 4, 5, 6. So let's get rid of this. We've got our 6 registers defined. We should fix that. Cool. So now we have our 6 instructions defined, right? And finally, let's define struct computer. And that is just going to have reg A, which will be a U size, reg B, which will be a U size. We need an instruction pointer, which will be a U size. And we need our instructions. So that will be a vector of instructions, like that. So now we've got our data structures. So the next thing we're going to want to do is how do we read our data from our input? Let's actually run this split right. Make this a little smaller, but we want to read this input in to our program here. And so we'll do a impl from string for computer. We need to start with a type error equals like that. And now we need to do a function from string. And the autocomplete is getting good at telling me exactly what I want. I think it might have, yep, it even imported the stuff we needed. I don't know why it works sometimes, but it worked this time, so that's good. And so what are we going to do here? We'll say like let mut instructions equals vec new. So we want a new vector. And right now we don't know the type. It'll figure that out for a second. So it's a for line in s.lines. And we'll say inst.push line.parse.unwrap. And we'll get that. So basically, we're going to write a from string for a line to go to an instruction. So we can just simply parse it here. We haven't done that yet, but we will. And then we're just going to return, okay, computer. Nice Radiohead reference. And then we can say reg A is going to start at 0. Reg B starts at 0. The instruction pointer starts at 0. And the instructions are the instructions. And now we've got everything we need except for, let's see, what do we like about this? P-U-T-E-R. And now we got everything we need except for this parse function. So let's come up here and define that. And we can do the exact same kind of things for enums that we did for structs, right? Now this is going to be, in some ways, like the hardest part of the program right here. So we'll do from string for instruction. And we'll need to do our type error equals like that. So we'll say a function from string. And so now how are we going to handle this? So we're going to take a single line. So we're going to get one of these lines right here, and we need to parse it. And so the first, let's see. So we'll say let mut tox. We're going to do like a split here again. I'll split this on that. So now we're going to get our tokens, and we can say let inst equals tox dot next dot unwrap. So we got our instruction. So this is always gonna be this first line, which is always gonna be the instruction, right? So we can now match on that and figure out what we're gonna do. So we'll do a match on inst. And so the simplest instruction actually, in some ways, because it only takes an integer, is this jump. And so I think we're going to parse that first. So we're going to say that if we're matching, if we get jump, we're going to say let dist for distance equals talks.next.unwrap. So now we'll have like this plus 22. We can say parse.unwrap. So now we should get an integer. And we say, okay, instruction, oops, not half, jump takes dist, that, and we don't need a semicolon because we're returning it, and we've built ourselves a jump instruction. Now it's not going to be happy because it says non-exhaustive patterns are not covered, so we have to have a default, right? But that's okay. Well, we're to work towards that. So I guess we can add that, right? If we get a default down here, we'll say panic unexpected instruction type, like that. Match arms without braces. I'm not sure what that means, but we can put braces there. Oh, we don't need a, that's what we need. There we go. So now we're happy, but we need more instructions, right? So the next thing we're going to do is we're going to say if it's HLF or if it's TPL or we're just going to do this so we can save some repeated code here, or if it's ink, we're going to let reg equals tokes.next.unwrap parse.unwrap. And what have we done here? Well, we want reg to be a register, and we've just said we want to be able to parse a token. So in this case, it's going to be like an A. And for these, it's just going to be, basically, it's going to be a letter, right? So we need to add a parse function that takes a string and turns a register. So we'll do that. We'll come back to that. But we can continue a little bit here. We can say match instruction, and now we can say if it's HLF, we return okay instruction half with reg. If it's TPL, we return okay instruction triple with reg. And if we are ink, we return okay instruction increment with reg. And now this one, even though we know at this point it has to be one of these three things, so it's always going to match this. We still have to provide our default, and we can say panic unreachable code. We put a comma there. Okay. So the problem is saying I don't know how to parse this into a register, and because we don't. So let's come up here and we will now add in how do we make a from string for this. So we'll say impl from string for register, and we'll say type air equals like that, and we'll say fn from string, and we'll say match s, and we have an a goes to okay self a. Now we get back, if we have an a, we get back a, and if we have that, we get okay self b. And we need to cover the other case, and that is again, we're going to be panic unexpected register s. And now I'll come back down here, and our parse function works just fine. It's happy. It's getting a register. Unnecessary parentheses. Let's get rid of those. Sweet. All right. So we've now handled the jump instruction, the triple, the triple, the half, and the increment. We're still not done. We've got some more instructions to do here. So next we have should we do? I guess we do well either actually JEIE, or JIO. For either of those, the next thing we're going to need to do, let's find one here, is this. Now this one's parsing is going to be a little bit different, right? So we still want to do, we still got our tokes, so we can still say let reg equals tokes.next, and we're going to have a dot unwrap dot parse dot unwrap. So again, this is going to take our next token, which returns an option, so we unwrap it to get the option. There better be a next token, or we want to panic. Then we want to parse it. So we're going to take that string and convert it to a register, which is going to return an option, which we need to unwrap. Now the challenge is when we get this right here, we have jump a comma, and we up here we're only matching on a. So we could do two things. We could come up here and take our s and like trim things off the end, or an alternative that's kind of cool is we could say or a comma, and we can come down here and we can say or b comma. And now either a or a comma is going to return the register a. And I think that's kind of slicker, so we're going to go with that. So now we're going to get down here and we should be, I don't know why it's not showing. Ooh, what's our error? Oh, our error is probably that we don't have expected Enum type. Oh, good, we haven't returned the right thing yet, I guess. So we're going to get back that. The next thing we do is we need to get, so we got our register, now we can get our offset. So we can say let offset equals talks.next.unwrap to get the next value. Now we parse it, this time into an integer, .unwrap. And now we should be getting, well, let's assume this is going to be our assigned integer. So now we can come down here and we can say match instruction. And if we have JIE, we're going to return okay. It's capitalized instruction for jump if even, and it takes two things. It'll take reg and it'll take offset. And if we have JIO, we're going to do the same thing. Okay, instruction, jump if one, and it's going to take reg. It's going to take offset. We need to close that. There we go. And finally, we do have, again, we only get into this branch if it's one of those two things. So this is just unreachable code. Grab right there. Save. And now everything is looking very happy. You can see up here, we are getting an I size for our offset. We're getting a register. Parse is just figuring it out based on what's expected down here. And I think we might have a working, implementation here, or at least how to create a computer. The only errors I'm seeing is that computer is not used, so and data is not used. So let's come down here to our main and we will create a computer. So we'll say let comp equals, and we want to go ahead and I guess we need to, let's see. So it's a couple things. We need to make it mutable. So we'll have a mutable computer. And we need if we're going to use the parse, we need to give it the type. So we'll say computer equals, and we'll say data.parse.unwrap, and call this comp. So now we've made a computer. Let's try to print it. This is going to take, we're probably going to have to go add our debug print to all our structures here, right? So if we run this right now, cargo run release, it's going to complain that it can't print computer because computer doesn't have a debug print. A computer cannot be formatted that way. So if we come up to our computer object, where's my computer? Probably under here, yep. So we can come here and we can say derive debug. And now computer has debug. But we also need everything inside of here to have debug. Which maybe vectors should have debug. Why is this complaining? Computer not be formatted using that. Add derived debug. I did. Did I spell it? D-E-R-I-V-E debug. Computer. Not save. Okay, so here we say instruction, the vector. Oh, because instruction. That's why. Because usize can all be printed with debug, but this instruction cannot. So if we need to come up to our instruction, and why did I actually just grab this while I'm here? And add derived debug, and we're also going to need to add it for register. Now, if we try to print this, we actually get back our computer. So our computer has a reg A, a reg B, an IP, and then a list of instructions. And you know, instructions are 47 long, so that's. And let's see, it ends with a jump -7. So it's kind of cool. You might ask, like, how does it ever end if it's got a jump -7? But it does have this jump +2, which would go to. Oh no, there must be a jump. Oh, this jump right here. This is how it ends. Jump if 1 in A. So when A has 1, it's going to jump up to the end. We've built a computer. Now we need to figure out how to run it. So let's start thinking about what functions we want to put on our computer itself. Let's see, we'll get the terminal smaller here. We don't need this for the moment. So what I want to be able to do, let's see, for our computer. So here we have, we'll say simple computer function run. It's going to just take mutable self, and it's going to return a usize, because we're going to return the value in B. That's what we want to know, right? Sorry, my alarm went off. So let's do this real quick here. We will say we're going to do a loop, basically. And in that loop, we're going to say let instruction, I don't know why we'll spell it out this time, equals self dot inst instructions dot self dot IP. So we're going to use the instruction pointer to get the instruction. And cannot move out of here because it does not implement the copy trait. What does not implement copy? Let's go ahead and give instruction copy, because I think it's going to be useful for keeping track of this. Otherwise, we're going to have some funky. Otherwise, we're going to have some funky ownership issues. Why are you unhappy now? Oh, because if we're going to copy, registers are going to need it too. And remember, we can't add copy without clone. So we'll add that too. And now we're back to just yellow, so that's good. Okay, so we've got our instruction. Let's match our instruction. This is where the enums are going to start to show really powerful. And we can say instruction half reg. So if we match that, we're going to. Now we need a way to take our register, which is like register A, and get back the computer's register. Does that make sense? So what we're going to do here is we're going to come up here and say fn, and we'll call it like get, and it's going to take mutable. I don't know if we need mutable. Let's see. We can just do. Let's just try self and register. So we're going to take in this register object, and we're going to return a pointer. We want to return a mutable pointer to a usize in this case, because we're pointing to this. We're going to get the pointer to the address of this thing so we can mess with it. So in this case, we'll say match r reg, and it's either going to be register A, in which case we're going to return mute self dot reg A, or it's going to be register B, and it's going to turn a mutable pointer to self dot reg B. And I think that's all we need. Now, again, this is really cool. Well, sorry, before we go, let's see what's wrong here. Okay, cannot borrow as mutable as behind it. Okay, so I think this is why we have to make this mutable. Yeah, okay. So what's cool is I don't even need to make the default case because there's only two types of registers it can be, and I've covered them both. Okay, so we're back down here. What we can do now is we can say, we want to say self.get on reg. So we're going to get our thing. We're going to say it plus, in this case, we're having it, so we're divide equals 2. And then we will self.ip plus equals 1. We're going to move the instruction pointer up. And what don't we like about you? It can be used on a d. It needs, we're getting a pointer, so we got to dereference it. So we will change that value. And I think we got it. So now we need to do an instruction. And we're doing, our next one's going to be triple, which is going to come with a reg. And for that one, don't forget the arrows. What are we going to do? So we're going to basically the same thing. Let's see, we'll grab this right here. And it's the only difference is instead of dividing by 2, we're going to minus or times equals by 3. Looking good. The next instruction we'll do is increment. And this one will literally copy this whole thing like that. And increment for onReg. And again, this one we're going to get it, and we're just going to plus equals 1. Okay, this is we're making good quick progress of this. So the next one we need to deal with is the instruction for jump. That is going to take off. And what we can do is this is a pain. So we'll do self.ip, and we're going to say, well, basically, what are we going to say? We just want to plus equals offset. And I feel like it should be that easy, right? But it's not going to like this. And the reason it is because we're trying to add a U size and an I size. And Rust is annoying as all get up about this. And I don't have a better way to do this other than there are some nightly build things I played with a little bit. But the short answer is what we want to be able to, what we actually have to do is we have to say, if off is greater than or equal to 0, then we can do self.ip plus equals off as U size, like that. Else, self.ip minus equals negative off as U size. I spent a bunch of time saying there's got to be a smarter way to do it than this, but I really couldn't find anything better, so we're going to go with this. And we're going to do, because we have these different jumps to handle, what we're actually going to do is come up here and say function jump mutable self. We're going to and an offset, I guess, off I size, and we're going to say just like that. Excuse me. And so now we can come back here and say for jump we want to self.jump off. Kind of morbid. Okay. So with that we can do the rest of the instructions. So let's see, we'll grab this will be jump if even, which will take a register and an offset, and we'll say if self.get reg, we say mod 2 equals 0. So if it's even, we jump to offset, and else we self.ip plus equals 1. So if we're, yeah, that looks perfect. And then the last thing we need here is there, we can jump if 1. And this one's the same thing, except for we're just going to say if this register equals 1. We're going to jump to the offset, otherwise we're going to be there. And I think that's it. So we're going to run our loop. Oh, we need a break. We need some way to end, because right now we don't end. So we'll say we're going to loop all of this. We're going to run the instructions until, I guess what we'll do is we'll say while self.ip is less than self.inst.len, something like that. What did I break there? Does that not have a matching one? It does. Self.ip is a usize. Expected. Oh, I don't return. Of course. So once we break out of the loop here, we're going to say self.regB. That solve all my problems? It solves problems. Nice. What are my issues here? Surprise, we are definitely using computers reg A and reg B. That's weird. We definitely call, run, and jump. I'm not sure what it's not saying. Oh, we don't ever call any of this. Okay, so now we can come down here. We can say dot run. There we go. Okay, so we might be done, at least with part A. Let's see, click here, cargo run, 307. I believe that is the correct answer. 307. Sweet. So part B. They're very happy, blah, blah, blah. Definitely not distract you. What is the value in register B after it's finished executing if register A starts as a 1 instead? So all we need to do here, we could just actually set it down here in main, but let's be a little bit like nice about it here, and we'll make a function reset mute self. A will be a usize, B will be a usize, and we will say self.a equals A, that's self.reg A equals A, self.reg B equals B, self.ip equals 0. So we've effectively now set the computer back to whatever state we want it to be in. So we can come down here now and say comp.reset, and we want A to be 1. We want B to be 0. And we can do, now we can just come down here and do comp.run. We save, we run, we get 160, which is the answer. So this was a fun challenge. Hopefully you enjoyed it, and I'd love to see your code if you have some way to throw it in the comments, or I guess hit me on Twitter. So thanks for sticking around to the end, and I'll talk to you next time. Bye.